everyone, and welcome to Network Playroom. In this video, we're going to continue where we left off in part 1. So as a quick recap, this is a new series where I'm turning my quick study notes into a somewhat more elaborate video format, so I can talk about the topics in a little more detail, and I don't have to cram everything in 280 characters or span them over multiple tweets. So we were talking about PGP, and I went over some basic concepts. And now we're going to move on to path vector functionality in PGP. By the way, you can still see the tweets, which I've turned into a blog post here on the right side of the screen, so you can follow along. Okay, so PGP peers exchange network reachability information called path vectors, which are made up of components called path attributes. Now, in simple and loose terms, a path vector protocol is a distance vector protocol with a complex metric. I believe I read this in an INE blog, and I thought it was a good way of expressing it. So let's discuss that a bit further. So other routing protocols can have a complex metric calculation, like EIGRP metric is based on the bandwidth and delay by default, although other factors can be included as well. And the metric formula is quite elaborate. However, the metric itself is a number, and the lowest metric is considered the best route. Now, in contrast, PGP has a multitude of path attributes attached to each route. And these attributes are compared and can be manipulated to influence the best path selection process. We will not go over the best path selection in this video, but we'll look at 3 path attributes to get an understanding of what is in a PGP update. So we'll look at AS path, next hop, and origin briefly. So let me just quickly demonstrate the concept here the differences between IGPs and PGP. So let's again draw a beautiful update packet here. So in the case of IGPs, so like for example EIGRP, you would just have a number here. Usually with EIGRP, it's something big. Let's just do like 286,000. Whereas with PGP, you would have a whole list of these different attributes, like I just mentioned, AS path. Then there's next hop, origin, and so on. So you have all these different things that are used in the best path selection process. Like these attributes are compared in a specific order, and whichever route wins the competition, I'll put that in quotes, is going to be the path used to reach that network. Okay, so let's talk about the AS path. Now, the AS path is a complete list of the hop-by-hop AS numbers to reach the destination network. Now, when the route goes through an autonomous system, that AS number is prepended to the AS path attribute. Now, the AS path information constructs a graph of the autonomous system to get to the destination. And the AS path is always loop-free. Because if a router receives a BGP update with its own AS number in the AS path list, it does not accept the update. I want to demonstrate that concept on the screen here, but I think this is a little bit messy, so let me get rid of some information here. Let's remove the AS numbers. Okay, so let's imagine another AS here. Let's make this AS 65003. And these are all connected. So let's say that this AS 65001 has a network here, 192.168. Let's say 0.0/24. Oops. Okay, I think my pencil might have run out of battery. No, I don't know what happened there. Yeah, so when this router sends out the network to the other autonomous systems, it is the AS path will contain that autonomous system. So 65,001. Now when this guy sends the route here, the AS path is gonna look like this. Oh no. So it's gonna prepend its own AS number. Okay, it's gonna be very messy here. Yeah, so then if the update comes back to AS 65001 from this AS, it's gonna look at it and see, oh, sorry, this is hard to explain. It's getting really crowded on the screen here. So it's gonna see its own AS number in the AS path, and it's going to ignore the update. It will not accept it. Hopefully that made sense. It was a little bit difficult to explain here. Leave questions in the comments if you would like more explanation about this concept. Okay, let's move on to the next hop attribute. So this one is pretty self-explanatory and simply refers to the IP address that should be used as the next hop to reach the destination. So again, when this route is advertised to the neighbors, it will include a next hop, I don't know, some X here, which will be added into the next hop attribute. Now finally, let's talk about the origin attribute. So the origin code tells how the route was sourced into PGP. So there are three main origin codes, or not main, only three origin codes. So number one is I for IGP, which means the route originated using the network statement. Then two, there's E for EGP, which means the route originated from EGP, and that protocol is the predecessor of PGP. It's obsolete and no longer used, so you should not see this origin code anywhere. And then number three is question mark for incomplete, which means the route originated using the redistribute command. So let's just write those down here quickly. So I is for IGP. Oops. IGP, which means the network statement. Then there's E for EGP. And this one is obsolete. So this is not used anymore. And then finally the question mark is for incomplete. And that meant the route was redistributed to PGP. Redistribute command. Okay, so that concludes the part about the path attributes. We'll probably come back to other path attributes in other videos, but now let's move forward to the next topic in our agenda today, which is PGP routing policies. Now, PGP allows you to define routing policies at the AS level, and because PGP uses so many path attributes, which the routing decisions are based on, the policies can be very granular. So the routing policies, I can't say that word. The routing policies can be more general, like having a universal routing policy for all routes, or more detailed down to a specific network. Now, PGP can also choose to advertise only particular routes to certain neighbors. I mean, the options are many. However, PGP can really only affect traffic within or leaving its own AS. Now, the internet follows a hop-by-hop routing paradigm, which basically means that how a neighboring AS routes traffic cannot be influenced, but how traffic gets to a neighboring AS can be influenced. So in other words, you can send your own traffic however you want, but once it's out of your AS, you have no control over it. So there are certain design goals when it comes to PGP interdomain routing, and the first factor is scalability. So again, the internet routing table is currently over 800,000 routes, and it's still growing, and PGP needs to be able to support this. Now, second, in PGP, you have to secure routing information exchange. Now, unlike IGPs, which can form neighbor adjacency simply by enabling the routing protocol, PGP doesn't trust its peers per se. So each PGP peer must be manually defined, and it is desirable to use authentication. Now, further, tight route filters are required. The best current practice is to require the explicit configuration of both import and export policies for ePGP sessions. You can read more about this in RFC 8212. And actually, iOS XR is already RFC 8212 compliant, and it should eventually get adopted to other iOS code as well. So in the other video, when we talked about these routers forming a PGP peering over TCP port 179, so this neighbor relationship has to be manually defined. So it's not like in IGPs, you insert the network command and everything just happens automatically and routers can discover each other. In PGP, you have to provide the neighbor address, and there are certain details, default settings, how the neighbor relationship, especially with PGP, is established. So there's something related to the TTL values and the directly connected check and so on. We'll go over those in another video. Now, finally, let's briefly go over the routing policies again. Now, although we discussed that you can only truly influence traffic within or leaving your AS, but it is still important to address both incoming and outgoing traffic flows. Now, each organization can decide how they want traffic to exit their organization, but influencing inbound or return traffic is based on peering agreements between the autonomous systems. So the only way to have control over incoming traffic is via route filtering. Like, you can choose to not advertise particular networks to certain PGP peers, and that way the PGP peers won't know that the network can be reached via that path. So in other words, it's like saying, you can get to this network through me, but I'm not going to tell you that. So if we look at this network again, so in PGP, I can choose to advertise this network to this neighbor, but not to this one. So in that situation, this AS will not know that the network can be reached directly, and it would have to go through this other AS over here. And again, as I mentioned, like, you can only really influence how you handle your own traffic and how it leaves the AS, but then you have no control over it. So there are certain ways that you can try to influence how traffic is forwarded. There are path attributes, like let's say you had 2 links between these autonomous systems. So you could indicate to the neighboring AS like, hey, I want you to prefer this path when you send traffic to me. But that is only a suggestion. You can't force that action unless you do some type of route filtering, if that makes sense. Again, you can leave questions in the comments and I will try to reply to you as best as I can. Okay, that concludes this video. So again, thank you for watching, and I'll see you next time.